Welcome. Today we're going to break down the absolutely brilliant engineering that powers some of the world's heaviest machinery. We're talking about the closed-loop hydrostatic system.
I mean, think about it, right? How is that even possible? Well, the answer lies in an incredibly elegant hydraulic system. And to really get it, we're not just going to look at diagrams, we're going to build one from the ground up, piece by logical piece.
Okay, so let's dive in. At its absolute heart, this whole thing comes down to just two main components: a variable displacement pump, which is going to create the flow, and a fixed displacement motor, which turns that flow into motion.
So here's how it works. Inside the pump, a part called a swash plate tilts. That pushes on some pistons and pressurizes hydraulic oil. You can see that high-pressure oil, we've got it in red, flowing over to the motor. This forces the motor's shaft to rotate, and that's what moves the machine. Then the low-pressure oil, here in blue, just completes the circuit and heads right back to the pump. It's a simple, super powerful closed loop, and get this, the pressure is determined entirely by how much work the motor is doing.
Okay, so how do you go in reverse? You don't need a complicated gearbox. It's so much smarter than that. The pump's swash plate simply tilts the other way. That's it. This instantly flips which line is the high-pressure side and which is the low-pressure side. And just like that, the motor spins in the opposite direction. It's an incredibly simple and direct design.
So what happens when you stop? When that swash plate is perfectly straight up and down, in neutral, it stops pumping oil. The fluid gets trapped in the lines, and since you really can't compress oil, it completely locks the motor shaft in place. We call this a dynamic brake, and it's a really powerful built-in safety feature.
So this seems like a perfect system, right? But there's a catch. And this brings us to our first big problem, which, in a fantastic twist of engineering, is actually a crucial feature of the whole design.
Believe it or not, the system is designed to leak. That's right, on purpose. Tiny amounts of high-pressure oil are allowed to seep out between all the moving parts, the pistons, the swash plate, everything. This is what lubricates and cools them. These little leaks are happening constantly in both the pump and the motor, creating something called case strain flow.
Now, all that leaking oil gets collected and sent back to a reservoir, which is great, but it creates a huge problem for our main closed loop. We're constantly losing oil. If we don't replace it, the pump is eventually going to suck in air, a process called cavitation, and it will literally tear itself apart. Not good.
So, to fix this constant loss of fluid, we need to add our first major component. We need a charge circuit.
And let's introduce the hero of this circuit, the charge pump. It's just a small, secondary pump, maybe a tenth of the size of the main one, and it has one job and one job only: pull oil from the reservoir and push it back into our main loop to make up for all those designed leaks.
And it's smart about it. It pushes this fresh oil into the low-pressure side of the loop. Now, to make sure it doesn't cause any problems, a simple little valve called a charge relief valve keeps this charge pressure at a nice, steady, low level, usually somewhere around 200 to 400 psi. So, problem solved, right?
Well, not quite. We've totally solved the leakage problem for when we're moving forward. But in fixing that one thing, we've created a brand new system-breaking problem the second we try to go in reverse. The instant we go into reverse, the high and low pressure sides flip. All of a sudden, our little charge pump is trying to force 200 psi oil into the main line, which might be running at thousands of psi. It's like trying to paddle a canoe against a tidal wave. It is just not going to work, and the whole system fails.
So how does the system possibly know where to send that charge oil, whether we're going forward or backward? Well, the solution is just wonderfully simple, and it's our next addition.
We add two simple one-way check valves. You can think of these like automatic gates. The high pressure from the main loop slams them shut, but the low pressure from the charge pump can easily push them open. This setup means the charge oil is automatically and perfectly routed to whichever side of the loop has lower pressure at that moment.
And this right here is a perfect example of engineering elegance. It's a completely passive solution. There are no computers, no sensors, nothing. The physics of the system itself solves this complex directional problem, making sure our loop is always topped off no matter which way we're going.
All right, our system is almost complete. It lubricates itself, it's bidirectional, but we have one last, and I mean absolutely critical, safety issue to solve. What happens when things go very, very wrong?
So imagine our machine drives straight into a solid rock wall. The motor stops instantly, but the pump, which is being driven by a massive engine, is still trying to cram thousands of psi of oil into that line.
The pressure would spike to catastrophic levels in a heartbeat, blowing hoses and destroying really expensive parts.
The solution is a pair of high-pressure cross-port relief valves. These act like a pressure ceiling for the whole system. If the pressure ever spikes above a preset limit, let's say 5,000 psi, the valve cracks open.
And instead of blowing up a hose, that dangerously high-pressure oil is safely rerouted or bypassed directly over to the low-pressure side of the loop, which protects the motor from damage. And of course, we need one for the forward line and a second one for the reverse line. This way, the system is safe no matter the direction or the load.
And there you have it. By starting with just a simple concept and then logically solving each problem as it came up, we've built a complete, intelligent, and self-regulating closed-loop hydrostatic system.
So let's just recap our journey real quick. We started with a basic loop that had a leak problem. We fixed that with a charge pump, but that created a direction problem, which we then solved with simple check valves. And finally, we solved the big safety problem of overpressure with cross-port relief valves. See? Each component has a specific logical job, building on the one before it.
And this is really why this all matters. The engineering principles here of managing pressure and flow in a self-contained, closed system, they're universal. Which leaves us with a pretty fascinating thought to end on. These systems are perfect for heavy machines here on Earth, but could these exact same principles work to power robotics in the hostile vacuum of space?